Dear students, I welcome you for the today's lecture. Today we are going to discuss the numericals based on the basic thickness calculation and the pressure calculation. Now already we have discussed related to the basic formulas for stress and the thickness. The circumferential hoop stresses or the hoop stresses, that is the Ft, which is equal to the Pd upon 2T. Now which are the circumferential stresses? For this I have already given a vertical joint for fabrication of the vessel. So when I am pulling in this direction, it is your axial stresses. This is the axial stresses when I am pulling in this direction. Your vessel is in the vertical direction. Along its axis, I am going to pull, which is going to give me the axial stresses. And these axial stresses are PD upon 4T. These are your axial stresses. This is what I am pulling from both the sides. This is along axis. When I have cut it from this section, it is going to look like this surface area. The stresses developed on this area, that will be taken as your axial stresses. Now I am pulling it in this direction. Your stresses are circumferential stresses, and which will be acting on this area and on this area. Previously, for axial stresses, it is this area that has been taken into account. For circumferential stresses, this and this area has been taken into consideration. So the stresses in the circumferential direction, that is PD upon 2T. Now when you compare these circumferential stresses and hoop stresses, the value of the circumferential stresses will be more than your longitudinal or axial stresses. So for the purpose of designing, the stresses which are more has to be taken for design purpose. When I am going to take the higher design stresses, then and only then my design will be the safe design. If I will consider the lower stresses, then there is a possibility that the failure will occur. And that is why I have to consider the stresses for the highest level, pressure for the highest level. So stresses developed in the vessel because of the pressure, because of the internal pressure that is taken on the higher side, and that will be considered as the design stresses. Then we have also talked related to the design pressure. This design pressure, which is nothing but the actual pressure, or you can say the operating pressure multiplied by the 1.1 times. That will be your design pressure. And this P in the given formula, that is PD upon 2T, that is nothing but the design pressure. Then D is the mean vessel diameter. Now this mean vessel diameter, when you take into account, there is the certain inside diameter as well as the outside diameter that can exist. So whenever there is a thickness that is provided. So I am increasing the thickness here. The outside diameter that is there and the inside diameter also that is there. So this has to be distinguished. D is my mean vessel diameter. Di is the internal diameter. So Di plus T. Di plus T, that will be equals to the mean diameter D. And similarly, the outside diameter DO, that will be is equal to Di plus 2 times the thickness. Di plus 1 times this side thickness and Di plus on the another side thickness. That is why it is Di plus 2T. And T is my vessel thickness. So I am knowing all these terminologies. This is the circumferential stresses, or we also call it the permissible stresses for that material. That means higher stresses is my permittive. It's a limiting one. उसके ज्यादा मैं स्ट्रेसेस नहीं कंसीडर कर सकता हूं, उससे ज्यादा जो स्ट्रेसेस एक्सर्ट हो गई उस मटेरियल पे, then it has to break, and that is why that is also called as the permissible stresses. परमिसिबल स्ट्रेसेस उतना ही वो परमिट कर रहा है, उससे ज्यादा जब स्ट्रेसेस एक्सर्ट हो गई तो इट हैज टू फेल, इट हैज टू ब्रेक, and the accident may takes place at that time. So the circumferential stresses which are considered as the design stresses in case of your cylindrical vessel. Because out of these two stresses, this PD upon 2T will give the higher value as compared to PD upon 4T. 4 से डिवाइड करने के बाद में वैल्यू ऑब्वियसली कम आने वाली है. Then the next thing is that for the cylindrical, PD upon 2 Fj, yes, when we are considering the cylindrical vessel, the design stresses will be taken as PD upon T, or the thickness in case calculation of thickness in case of cylindrical vessel, that is PD upon 2Fj. And for a spherical vessel, now in case of a spherical vessel, it is only the longitudinal stresses which exist, because whenever there is a complete sphere that is available and you can cut it from any side, so at that situation only the longitudinal stresses that is going to exist. And so design purpose in case of a spherical vessel, that is your PD upon 4Fj. So when we are considering the cylindrical vessel thickness calculation, we are using the formula PD upon 2Fj, and in case of a spherical vessel, we are considering only the longitudinal stresses, because that is only the longitudinal stresses that exist in case of a spherical vessel, which is nothing but PD upon 4Fj. Now we are writing the stresses or the thickness in terms of a internal diameter and in terms of a external diameter. So D is equal to Di plus T, and D which is equal to the Do minus T. So this can be substituted in terms of this basic equation of PD upon 2Fj, and this can be simplified to obtain T which is equal to PDI upon 2Fj minus P. Similarly, when we write in terms of the DO, this is in terms of the DI, because we are substituting here D which is equal to the Do minus T in this basic equation, you will get a relation in terms of a Do. So this thickness T, which is equal to P dO upon 2Fj plus P. So one has to remember these small equations in terms of the di and in terms of the do. Then the J, joint efficiency, and the corrosion allowance, that has also to be taken into account. So when you write the joint efficiency J, the equation incorporates PD upon 2Fj, and we are also adding the corrosion allowance C in that, so it becomes plus C. So all the above equation, that is in terms of the DI and in terms of the DO, that is the addition of the plus C, in all the equation. In general case, the C corrosion allowance, that is taken as the 2 millimeter thickness. For general purpose, if the material is highly corrosive or the atmosphere in which the vessel that exists, if it is highly corrosive, then this corrosion allowance that can be increased to say 4 millimeter also. So now looking at all these different formulas, we can do the different permutations and combinations for numerical in this case. That is the numerical for the vessel or the shell thickness calculation. In that, we can consider for the cylindrical vessel and spherical vessel. For cylindrical vessel, we are having the formula PD upon 2Fj. For spherical vessel, the thickness will be is equal to PD upon 4Fj. Then we can also talk about the effect of joint efficiency. That is whether it's a class A, class B or class C. So depending on this class, that is the J joint efficiency will have the value of 1, 85%, 70% or 50%. We can see the effect of the joint efficiency on the calculation of the thickness. The next is the corrosion allowance. Whether I am adding the corrosion allowance, what is the effect on the calculated thickness? And without adding the corrosion allowance, what will be the value of thickness? That distinction I have to do it. Now, D is your mean diameter. So I can do the calculations with the mean diameter. I can do the calculations with the internal diameter. Also, I can do the calculations with the outside diameter. Means it can be either D or DI or DO. And there can be also the variation of terminology, that is the operating pressure or the design pressure, what is specifically mentioned in the numerical. Because my design pressure, which is equal to the nothing but 1.1 times the operating pressure or the actual pressure, and in the formula of PD upon 2Fj, where I have to consider the design pressure. And so all these numericals, they are related with these 9 different terms. And in addition to that, this is all the calculations related to the thickness. And there are certain calculations where the pressure that can be calculated, the vessel already exists with me. I can also calculate the pressure at which the available vessel of a specified diameter and thickness is available. What pressure that vessel can sustain? That means the calculation of a pressure. So all these are my permutations and combinations related to the calculation of the stresses, thickness and the pressure. because my formula that incorporates PD upon 2FJ. So जितनी सारी टर्मिनोलॉजीज है इसमें, वो सारे टर्मिनोलॉजीज का एनालिसिस करने का है। फॉर्मूला एक ही है, बट न्यूमेरिकल्स कितने टाइप के हैं? 9-10 टाइप के न्यूमेरिकल्स हैं, एक ही फॉर्मूले पे बेस्ड। एंड दैट इज व्हाई वी आर गोइंग टू डू द एनालिसिस। We are not focusing in this subject more related to the development of the basic equations, but we are trying to do the analysis. This subject helps us to analyze the different situations, complexities, how you are going to increase the complexities. That is the beauty of this subject. So that जो कुछ दिया है मेरे को, उसका एनालिसिस में किस अलग अलग एंगल से कर सकता हूं, दैट इज ऑफ प्रीफरेंस। So I can do the analysis related to the cylindrical vessel, spherical vessel, then the effect of joint efficiency, the corrosion allowance effect, the mean diameter. When we talk related to the diameter, it is the mean diameter, internal diameter and the outside diameter. Besides that, talking related to the pressure term, that is the pressure, operating pressure and the design pressure. So all these different considerations have to be taken. So one by one we will see the numericals associated with this. So first numerical, this is the most simplest numerical where we are considering the basic formula of PD upon 2T. Now looking at this formula, the stresses, that is your circumferential stresses or the hoop stresses, which is equal to the PD upon 2T, and this is considering for the cylindrical vessel because it is giving the higher value. Now this formula incorporates the terms stresses. So I will require the basic stresses for that material. Then what will be my operating pressure or the actual pressure? What is the mean diameter, or if I have been provided with the internal diameter or external diameter, then I will be able to calculate the thickness. So let us see what is given in this numerical. Calculate the wall thickness. So I have to calculate the wall thickness. Then for a cylindrical vessel, we are having the circumferential or tangential or the hoop stresses which are giving the higher values. So the pressure which is given, that is the 3 kgs per centimeter square. In this case, it is the actual pressure or the operating pressure, that is what is mentioned. Then the diameter of the vessel that is given. So pressure that is given, D is the diameter that is given, and the permissible stresses of that material that is also given. In case of a cylindrical vessel, the permissible stresses are nothing but your circumferential stresses. For a cylindrical vessel, the permissible stresses are your circumferential stresses because these are the higher stresses. So by simply substituting the different values in this formula, basic formula, so let us calculate the thickness. So thickness, that will be equals to which is equal to the PD upon 2F. So this is my formula. Now pressure, this is the design pressure. So my actual pressure that is given as the 3 kgs per centimeter square. 1.1 into 3, that is the design pressure. This is the units kgs per centimeter square. Then the vessel diameter D. D is the mean vessel diameter, that is what is mentioned in this numerical, because this specifically internal diameter or external diameter, that is not mentioned, and that is why we are considering it as a mean diameter. So we, as a mean diameter formula, we are using the D. This is the 2000 millimeters, that is what is converted as the 2-meter diameter. Then upon 2 into the F, this is the 2 into the F, this is the stresses, kgs per centimeter square. Now here writing the units is very much essential. Then and only then your answer will be correct, or else you will do the mistake in the units. मिस्टेक कहां पे होने वाली है? यूनिट्स में. I have written the pressure in terms of kgs per centimeter square, stresses in terms of the kgs per centimeter square, because they will get cancelled, and here I can write in terms of centimeter or in terms of millimeter also the vessel diameter. So here I have written the vessel diameter in terms of a millimeter. So my thickness, that comes as the 3.3 millimeter. Now this is the theoretical thickness which I have calculated. So this plate thickness, will it be available in the market? That is the question. So 3.3 millimeter thickness plate is not available in the market. Then what is available in the market? Either I will get a 3 millimeter thickness, or I will get a 4 millimeter thickness plate. That is the limitation. So I can switch over to the 4 millimeter thickness plate. But for the welding purpose, I require the 5 millimeter thickness plate. If I am going to use the less millimeter thickness plate for the welding will not be that much effective, and there is a possibility that the cracks may develop in the process of a welding, and that is why the higher thickness of 5 millimeter that is taken for all basic consideration of calculations. So 5 millimeter thickness plate will be selected for the fabrication of vessel, even though I have theoretically calculated the value as 3.3 millimeter. I will not use this 3.3 millimeter thickness plate because of the welding issues. So minimum thickness for fabrication of the vessels, that is taken as the 5 millimeter. So in this numerical, we have basically calculated the thickness and the selection of the final selection of the plate thickness for fabrication of a cylindrical vessel. Right? Now coming to the next numerical. In this, we are going to calculate the thickness for a cylindrical vessel and for a spherical vessel. So a vessel having the 1.6 meter outside diameter, in this case the outside diameter that is mentioned. So I have to use the formula in terms of a DO, and is operated at a pressure of 5 kgs per centimeter square. The permissible stresses of material for fabrication is taken as 1000 kgs per centimeter square. The joint efficiency that is also mentioned in this numerical, that is 85%. Then calculate the thickness required for the cylindrical vessel and the spherical vessel. So, which vessel should be selected for operation? I have to select a vessel which will be suitable for operation, whether it's a cylindrical vessel or whether it's a spherical vessel. Even though the thicknesses, for that purpose we will first calculate the thickness and then we'll select the vessel. Now the design pressure that is mentioned as 5 kg, operating pressure that is mentioned as the 5 kgs per centimeter square. So the design pressure that will be taken as the 5 into 10 to the power 5 into 1.1, which is 5.5 kgs per centimeter square. So this is my design pressure. What is my vessel diameter? D is given as 1.6 meter and which is mentioned in terms as a outside diameter. So I have to use the formula PDO, that is in terms of a outside diameter, that is PDO upon 2FJ plus P. So the thickness pressure that is calculated as the 5.5, that is nothing but 1.1 times the actual pressure multiplied by the DO, that is the outer diameter, which is mentioned as 1.6 meter, that I have converted into the millimeter, that is 1600 millimeter. This pressure is in terms of the kgs per centimeter square, that is 5.5 meter, divided by 2 into the F. F is nothing but the 1000 kgs per centimeter square. Then J is the joint efficiency, which is mentioned as 0.85%. So whatever the stresses on the material that will be there, they will be reduced by that factor of joint efficiency. So 1000 into 0.85 plus the P pressure, that is the design pressure. So after calculation you will get the thickness as 5.16 millimeter. Again, the thickness of plate 5.16 millimeter is not available in the market. So I have to go for the next higher value of the thickness, which is nothing but the 6 millimeter standard thickness plate has to be selected. That is the selection of a plate thickness for fabrication of a cylindrical vessel, because for cylindrical vessel it is the PD upon 2FJ, two factor is there. Now in case of a spherical vessel, my formula becomes PD upon 4FJ. This is PD upon 4FJ for the spherical vessel. So this thickness calculation in terms of the outside diameter will become PDO upon 4FJ plus P. For the cylindrical vessel, the formula is PD upon 2FJ. And for the spherical vessel, the formula is PD upon 4FJ. This is for the spherical vessel. And this formula PDO upon 2FJ is for the cylindrical vessel. So for spherical vessel, I will do the calculation pressure as 1.1 times the design pressure. That comes as the 5.5. Then DO, which is outside diameter, that is taken as 1.6 meter, which is nothing but the 600 millimeter. Then 4 times the stresses, material stresses, F is nothing but 1000 kgs per centimeter square, that is the unit for pressure. J is my joint efficiency, which is nothing but 0.85, and the P, the design pressure, this is 5.5. So my thickness that comes as the 2.58 millimeter. Again, I cannot use the thickness of 2.58 millimeter. So next available standard thickness is 3 millimeter. But for the purpose of welding, I have to select the minimum thickness as the 5 millimeter thickness has to be selected. Now, for a cylindrical vessel, the vessel thickness that comes as a 6 millimeter. For the spherical vessel, the vessel thickness that comes as a 5 millimeter. This is selected depending on the available thickness. But what actually that is calculated, that is this 2.58 and 5.16. This is nothing but the 2 times the spherical vessel thickness will be is equal to 2 times the thickness for spherical vessel will be is equal to the thickness for the cylindrical vessel. So because here we are dividing by 4, here we are dividing by the 2, and that is why this factor of 2 that is compensated from this basic formula of the thickness calculation. So for a cylindrical vessel, the thickness is less. For a cylindrical vessel, the thickness is more. Spherical vessel की thickness कम है, cylindrical vessel की thickness ज़्यादा है. But for fabrication of a cylindrical vessel, it becomes more and more difficult. स्फेरिकल वेसल का फैब्रिकेशन करने के लिए मेरे को अलग अलग कटिंग्स करने पड़ते हैं. लाइक दिस आई हैव टू डू द कटिंग्स. Such type of the shapes I have to cut, I have to arrange them properly, and then I have to do the welding. Then and only then the spherical vessel that can be fabricated. However, in case of a cylindrical vessel, it is the simple sheet bending that is to be done. ये sheet को मैंने सिर्फ bend करना है, and then I have to do the welding. And this process of fabrication of cylindrical vessel is much more cheaper than cutting the sheets in this spherical vessel format and then welding. So many welds will be required. सारे लोगों ने छाता देखा हुआ है और छाते के जैसे शेप्स आते हैं, उसी टाइप के शेप्स मेरे को कट करने के हैं. Then and only then the welding that is possible for a spherical vessel. So it is similar to my umbrella cuttings or umbrella shapes. So the thickness vessel fabrication cost is much higher in case of a spherical vessel, and that is why even though the calculated thickness or the selected thickness for a spherical vessel is much less than the thickness for a cylindrical vessel, I am going to select a spherical vessel which will be more cheaper than the spherical vessel. So it can be seen that the thickness required for spherical vessel is 50% of the thickness required for cylindrical vessel. But the spherical vessel offers the uniform stress distribution also. But the cost of fabrication is too high for a spherical vessel. And therefore, for economic reasons, the cylindrical vessel with 6 mm standard plate thickness is selected. So this is the related to the second numerical which we have already discussed. Whether it's a cylindrical vessel or spherical vessel that we have talked. We have also talked the mean extra outside diameter vessel. We have also used the joint efficiency. We have also used the operating pressure and the design pressure term. Now the effect of joint efficiency that is to be studied. In this numerical, the joint efficiency is taken into consideration So class A vessel 100% joint efficiency, class B vessel 85% joint efficiency, class C vessel with 70% joint efficiency and class C vessel with the 50% joint efficiency. चार cases है अपने पास. So what is the actual numerical that is mentioned? The outer diameter, a vessel which is having the outer diameter as 1.3 meter, DO mentioned किया हुआ है. Height of the vessel that is also mentioned, but our formula PD upon 2FJ that doesn't incorporate the height. So the given provided data is of no use for me. Then it is subjected to an internal or the operating pressure of 12 kgs per centimeter square. यहाँ पे इंटरनल और दी ऑपरेटिंग प्रेशर मेंशन किया हुआ है, डिजाइन प्रेशर मेंशन नहीं है. सो आई हैव टू मल्टीप्लाई बाय 1.1 फैक्टर to get the design pressure. And if the vessel is fabricated as the class B vessel, the joint efficiency is 85%. If the vessel is fabricated as the class C vessel, the welded joint efficiency is 70% and 50%. If the vessel is provided with a strip along the longitudinal joint, the efficiency is taken as 100%. Then calculate the vessel thickness under all these different conditions and find out how much is the percentage of material saving in the welding strip along the longitudinal joint. The allowable stresses for the material that is mentioned as 1020 kgs per centimeter square, and the corrosion allowance that is also provided in this case as the 1 millimeter. So all these complexities in the numerical that are increased. First, the design pressure P, I have converted it from the operating pressure of 12 kgs per centimeter square to 13.2 kgs per centimeter. Then the outside diameter formula I have to use, that is PDO upon 2FJ. This is for the cylindrical vessel formula. Then one by one, taking into the joint efficiency values, I am going to calculate the required thickness. So for the class B, the joint efficiency is 85%. So thickness that will be calculated as the design pressure PD into the D, the diameter is 1.3 meter diameter, which is nothing but the 1300 millimeter divided by the F, 2 times F into the joint efficiency plus the pressure P. This is plus this plus is total plus 1. So that comes as the 10.82 millimeter. Again the 10.82 millimeter thickness plate which is not available in the market. So 12 millimeter standard thickness plate I have to select. Now similarly for the class B, the joint efficiency, the thickness calculated will be 12.96. 12.96 thickness plate is not available. Even the 13 millimeter thickness plate, that is also not available. That I have to select it to the 14 millimeter thickness plate. After 10 millimeter thickness plate, the availability, that is in terms of the multiples of the 2, 10, 12, 14, 16, 18, 20 millimeter thickness plates are available. The next, I can do the calculation with the 50% efficiency. The thickness value that comes as the 17.6 millimeter. I have to select it for the 18 millimeter thickness plate. Then for the class A joint efficiency, 1, the thickness that comes as 9.3. So 10 millimeter thickness plate that is calculated. Now the percentage savings in the material depending on the joint efficiency. So J, which is equal to the 85%, the 12 millimeter thickness and the 10 millimeter thickness, that gives the 16.67, then 28.57 for 70% joint efficiency, then for 50% joint efficiency that comes as 44%. So 10 millimeter, 12 millimeter, 14 millimeter and 18 millimeter thickness plates will be required. And accordingly, the percentage savings of the material will be from 16 to 44%. Now the last numerical that is related to the calculation of the pressure, that is a cylindrical pressure vessel 2 millimeter internal diameter is to operate at a pressure of 4 kgs per centimeter square. The permissible stresses of material is 960 kgs per centimeter square. Then the welded joint efficiency is 85%. Calculate the thickness required for the vessel. If the vessel is fabricated in spherical form, what maximum pressure will it be able to withstand? पहले तो मेरे को सिलेंड्रिकल प्रेशर दिया है, उसका ऑपरेटिंग प्रेशर दिया हुआ है 4 kgs, उसका डायमीटर दिया हुआ है, उसके परमिसिबल स्ट्रेसेस दिए हुए एंड जॉइंट एफिशिएंसी दिया हुआ है. So I will be able to calculate the thickness for this cylindrical pressure vessel. Then calculate the thickness required for the vessel if the vessel is fabricated in a spherical form. So जो thickness आती है वही thickness का मैं spherical vessel fabricate करता हूं तो वो मैक्सिमम कितना प्रेशर सस्टेन करेगा. That is, what maximum pressure will it be able to withstand? So one by one we will calculate the thickness for a cylindrical vessel first. So design pressure is the 4 kgs per centimeter square, that is the actual pressure, multiplied by 1.1, which is 4.4 kgs per centimeter square. Writing units is very much essential. 4.4 kgs per centimeter square. Then in this numerical di, that is the internal diameter that is mentioned as the 2 meter internal diameter that is mentioned. So this is 2000 millimeter has been converted to that. Then F is 960 that is mentioned in this case, is the permissible stresses for the material is 960 kgs per centimeter square. So 2 times into 960 into the joint efficiency, which is 85%, minus the P pressure. In this numerical, the corrosion allowance that is not mentioned, and that is why we have not taken into account the any corrosion allowance. So the thickness that comes as the 5.4 millimeter. Now 5.4 millimeter thickness plate which is not available in the market. So I have to go for the 6 millimeter thickness plate for a cylindrical vessel fabrication. Now I have calculated the 6 millimeter thickness plate for a cylindrical vessel where I will be able to withstand the pressure of 4.4 kgs per centimeter square, or the operating pressure of 4 kgs per centimeter square. Now with the same thickness I am going to calculate the pressure which will be sustained in a spherical vessel. So spherical vessel, the formula is PD PDI upon 4FJ minus P. So substituting all these values and calculating the required pressure, that comes as 8.8 kgs per centimeter square, which is nothing but the 2 times the pressure that is required for the cylindrical vessel. Cylindrical vessel, it is the 4.4 millimeter. For spherical vessel, the vessel pressure, it can withstand up to the 8.8 kgs per centimeter square. So this is, from this we can calculate the conclusion that the spherical vessel of the same thickness as that of cylindrical vessel is able to withstand twice the pressure. It is twice the pressure which we can withstand with a spherical vessel.